Good afternoon, everyone. Myself, Dr. Prateeti Chakraborty. I'm Assistant Professor of Chemistry. I'm from Calcutta, Bangabasi College. Today, I'm going to share some of my research work with all of you. And it is the chemistry of zinc complexes with some different non-covalent interactions. So before going into my discussion, and I would like to just discuss something about what is non-covalent interactions. Nowadays, so many researchers are interested in study of some non-covalent interactions, and they are often ubiquitous in nature. And these interactions are much significant, and they can influence the structural topology, physical and chemical characteristics of the system. The most important example is very known to us, that is the water, which is the basis of our life. And the structure of water is governed by the non-covalent interaction. Okay, it is very interesting for us. And the other one is the biological, that is the structure of DNA, which carries all the genetic information. And that structure of DNA, double helical structure, is being stabilized by the hydrogen bonding between the bases present in the DNA. So it is very interesting to study those non-covalent interactions. There are so many research is going on the protein structure and the non-covalent interaction, which is being studied by all the researchers, but there are very few researches on the coordination complexes. So I'm going to discuss on that only in this platform. And for getting a brief idea, so the fusion of experimental and theoretical studies needed. Now, why I have chosen zinc? Zinc is biocompatible. So that means if we can study some non-covalent interaction of zinc complexes, we can study their biological applications also, like as the antimicrobial activity, anti-cancer activity, and so much. And it is the second most abundant trace element next to iron. Okay. And the other one is that it is silent towards all the common spectroscopic technique, and most interestingly, it can adopt several coordination number and several geometry can be adopted, which is very much essential for governing some non-covalent interaction, and different structure can be generated. The ligand structure can be altered, the electronic properties of the ligand can be altered. And it is the ability to enhance the photoluminescence efficiency of some organic luminescent ligand. Next, coming to the ligand, that is a metal I have chosen zinc. And what about the ligand? The sheep bases are the most fascinating ligand for us, coordination chemists. And they have chosen to strengthen the possibility of observing several interesting non-covalent interaction like cation pi interaction, anion pi interaction, CH pi interaction, etc. And the Lewis acidity of zinc may also be helpful for us to study or to influence the several non-covalent interaction, and as well as the physiochemical properties of the complexes. In my study, I have chosen some pseudohalides like thiocyanate, azide as co-ligand to utilize their versatile mode of coordination, which may lead to interesting structural features as well as some unusual non-covalent interaction. The first word that I will discuss here, that is the comprising of this ligand. Okay, here I have just chosen the ligand, and the R group will be different in all the cases. It is methyl tertiary butyl as well as chloro. The preparation method is very simple. Just by starting the ligand and acetate and sodium thiocyanate, we are getting the ligand complex counter anion. One interesting point is to be noted here that whenever we were studying this in lab, we were not getting any complex, any solid complex that may not be crystal, not any solid complex in presence of ligand and zinc acetate. But as soon as we are adding the sodium thiocyanate, we got crystal in every case, that is irrespective of any R group. Okay, so this is an interesting point which I will discuss later on. By XRT, we have studied the structure. This is the structure of all the complexes. And here we can see that zinc is penta-coordinated in all the complexes, and it has a geometry in between trigonal bipyramidal and square pyramidal. Okay, all the crystal structures are stabilized by some weak CHO hydrogen bonds, mainly involving the oxygen atoms of the morpholine moiety and the acetate group, and the intermediate adjacent position is being filled up by the zinc tetrathiocyanate moiety. We have studied the absorption spectra of the complexes in methanol. And here we can see that the lowest energy band corresponds to the 390 nanometer, which is due to the pi star excitation that we have already explained in. And the maxima will remain same with we can change the solvent polarity, but the maxima will not change. Okay, so the polarity of maxima, the polarity of solvent is not affecting the absorption spectrum. The complex 2 and 3 exhibits higher absorption than complex 1. It is just clearly visible in the spectrum, and it is due to the dimeric nature of complex 2 and 3 in solution. We have studied the fluorescence spectroscopy of the complexes, and this is the fluorescence spectra. Also, the fluorescence decay was studied here. We have studied the phosphorescence spectroscopy of the complexes. This is the phosphorescence spectroscopy. And this table summarizes all the data of the fluorescence and phosphorescence. Here we can say that the phosphorescence quantum yield is highest for the tertiary butyl complexes. It is highest for the complex 2, that is the tertiary butyl complex, then methyl, and then chlorine. Phosphorescence lifetime is the ultimate factor governing the phosphorescence quantum yield efficiency of the complexes. If we look into the singlet state lifetime, we can say that there is 2 components in the lifetime, and the contribution of all the cases is different for the different complexes. It is 88% for the complex 1, that is the methyl complex, and it is only 54% for the tertiary butyl complexes. So this is due to presence of 2 conformer in the solution. That's why we are getting just 2 component of the lifetime. And one interesting point was that all the complexes were exhibiting phosphorescence at room temperature, and it can be explained that by assuming that either the ligands are rigidly held by the metal ions in all the complexes, or there may be some distortion in the geometry of the triplet state, or both of them. To confirm our study, we have performed anisotropy, that is a time resolved anisotropy study, and from that decay we again can just observe the previous one, the rotational correlation time. That is, the complex 2 and 3 has just double rotational correlation time than complex 1, which again indicates that complex 2 and 3 exist as dimer in solution. Next is we have performed a theoretical study to just support our all those experimental data, and this is the spin density distribution plot, and which indicates the lesser participation of zinc atom in the emission process. And to know about the structural part, we have just optimized all the structures and analyzed the influence of para-substituent as well as different interaction in governing the solid state structure. And this is the molecular electrostatic potential of titanium tetrathiocyanate anionic moiety. We have just replaced that moiety by a neutral titanium tetrathiocyanate moiety. Okay, so and next we can see that there is a sigma hole at the sulfur atom and as well as a negative belt around the sulfur atom, so which it can participate in both hydrogen bonding as well as chalcogen bonding. And the complex has one cationic counterpart and the anionic counterpart, and both of them are interacting with each other through some non-covalent interaction. Next, we have studied the interaction energy. What are the different non-covalent interaction energy? This is the sulfur oxygen chalcogen bonds. The interaction energy is minus 143 kilocalorie. And for hydrogen bond, it is minus 1. And the lone pair pi hydrogen bond is nearly minus 180 kilocalorie. Okay. Now, it is for the anion pi interaction. Methyl group in 1. You can see in this picture also that the titanium tetrathiocyanate moiety is also involved in such kind of weak interaction in all the 3 cases. It is for all the 3 complexes where we have just changed that zinc tetrathiocyanate moiety with titanium tetrathiocyanate moiety. Methyl group in 1 establishes weak CHO interaction, tertiary butyl into CH pi interaction, and chloro group interaction is halogen bonding interaction. One thing we have to mention, we note that the tertiary butyl group is a bulky group. Okay, so for its bulkiness, it is unable to participate in pi-pi stacking interaction, and all those interactions are completely influencing the structure of all the 3 complexes. Next, we have studied the dimerization energy. What we have done basically, we were interested to know the role of R group in our structure formation as well as other properties. We just replaced the R group with hydrogen. That was the simplest molecule. What we observed then, that relative interaction energy reduces drastically for tertiary butyl group, but it is not that much for chloro and methyl group. So we conclude that the complex 1 and complex 3 contribution of pi-pi stacking interaction is present, but it is not possible in complex 2 due to tertiary butyl group. This is the highlights of that work. The next work that we have done is just a very simple work. We have taken 2-benzoyl pyridine and amine, and we have just synthesized all the complexes, and we have synthesized 4 complexes, but I will discuss here only 2 in presence of metal perchlorate and thiocyanate. All of them were mononuclear one. And the complexes are mononuclear, and zinc is pentacoordinated and having a distorted square pyramidal geometry. The complexes form dimers along a particular axis, and it is only for the pi-pi stacking interaction between the coordinated pyridine rings. The phenyl moiety of the ligand and the methylenic hydrogen of ethane backbone are involved in CH pi interaction. It is applicable for both the complexes. Okay, this is a supramolecular interaction in complex 1, and this is a supramolecular interaction in complex 2. Okay. Now we have studied the Hirschfeld surface analysis, and for both the complexes, and fingerprint plot we have studied, and fingerprint plot of 1 shows a diffuse blue region in top corner, which is indicate the lower packing efficiency of 1 than 2, and different red circles in plot shows the CH pi interaction. And this is the contribution of different intermolecular contacts for the surface area, and this is the percentage contribution of different intermolecular contacts for Hirschfeld surface areas of complexes 1 to 4. And here we can say that, this complex is, for complex 1, the hydrogen-hydrogen interaction is maximum, and the carbon-carbon interaction is minimum for complex 1. Okay, but the OH interaction is absent in both the complexes of that complexes. We have performed a theoretical study, and the theoretical study says that self-assembled dimers in solid state is stabilized by a combination of 2 interactions involving these 2 aromatic rings, pyridine rings, and as well as the pseudo-halide ligand. The coordinated pyridine rings form an pi-pi stacking interaction, and aromatic hydrogen atom of pyridine interacts with the pi system of pseudo-halide. And similarly, a double CH3 pi interaction is happening in complex 2. Okay, and we have computed the interaction energy in the hypothetical dimers. All of these are hypothetical one, it is not the actual one. And where the pseudo-halide ligands are replaced by just hydride ligand, that we have done in earlier case also. Just pseudo-halide ligand is replaced by hydride ligands to know the contribution of CH pi interaction. The compound 1, the interaction energy is minus 3.2. Okay, and it is for CH pi interaction, which is large in compared to pi interaction. For complex 2, each CH pi interaction is nearly 6 kilocalorie. Okay, nearly 6 kilocalorie. That is similar in energy of each CH3 pi interaction. And this interaction energies are larger than those previously reported for any kind of coordination complexes. By calculation of this interaction energy, we can conclude that the influence of metal coordination upon pi stacking is very small and unfavorable. But for for structure geometry, the CH3 pi interaction is very much favorable. To get into more detail or more deep insight into that matter, we have calculated the molecular electrostatic potential surface. What we have done, just we have taken zinc, azite, NCO, NCS, and NCSE, all those several Zn, PS2 type, pseudo-halide type complex, all the pseudo-halides we have taken. And electrostatic potential for azite, if we can see that at central atom of pseudo-halide is positive for azite and it is negative for NCSE and NCS whole 2. Okay, that is a selenoisocyanate and thiocyanate. It is a negative potential. In complex 2, the CH pi interaction involves the terminal nitrogen atom of the ligand, and in 2 it involves the central carbon atom. Okay, so that was the conclusion, and this is the highlights of my work that I have already discussed. That is the role of non-covalent interaction is responsible for the crystal packing of the complexes in presence of different pseudo-halides. And the ability of the pi system depends on the nature of the pseudo-halide, which is completely demonstrated by the molecular electrostatic potential calculation. And I would like to thank University of Calcutta for providing the facility of crystal X-ray diffractometer and DST phase program. And this work was supported by DGICYT of Spain, one of my collaborators. And these are the references. And lastly, I would like to thank the organizer for providing me the opportunity to share my work with all of you. And thank you all for your kind attention. Thank you so much.